Hello, and welcome to our video on our grating light valve and planar light valve technology and their applications. Silicon Light Machines is an optical MEMS modulator supplier with decades of experience. In this talk, we will be introducing our grating light valve and planar light valve technologies. Our products include 1D and 2D true grayscale amplitude modulators, as well as full phase modulators, all with high speed and high power handling for UV to NIR wavelengths. We are excited to introduce new products, including a large aperture linear planar light valve amplitude modulator for material processing, as well as a new real-time controller for direct communication between the module and the computer. Silicon Light Machines is a wholly owned subsidiary of Screen Holdings, who utilize our technology for their state-of-the-art precision equipment in the silicon processing and graphic arts industries. Silicon Light Machines also supplies optical modulators and solutions to numerous customers for many different applications, and we are always happy to work with new partners. The grating light valve, or GLV, is a ribbon-based diffractive technology for high-speed, true grayscale amplitude modulation with high power handling for UV to NIR applications. Aluminum silicon nitride ribbons are electrostatically actuated to create diffraction grating pixel elements. Inactive ribbon elements act as a mirror. By deflecting every other ribbon, light is diffracted into a first order. Varying the deflection diverts more or less light, acting as a light valve. Amplitude modulation is achieved by allowing only the first or zeroth order. An example of zero-order filtering is shown on the top right. The GLV creates a relative phase delay of light through the ribbon actuation. By operating every ribbon individually rather than as static active line pairs, the GLV becomes a uniquely high-speed phase modulator. Amplitude modulation requires a quarter wavelength deflection, while full phase operation requires 1/2 wavelength. The planar light valve, or PLV, is a new technology that utilizes piston motion, much like the GLV. A center surface is deflected while the surrounding remains static, diffracting light into a circular first order. The PLV retains the high-speed grayscale advantages of the GLV. However, the two-dimensional surfaces allow for larger apertures for higher throughput and power handling, as well as simple spherical optical designs. We are currently developing a 8192 channel module. The PLV may also be operated in a linear manner, similar to the GLV, with a device we call the linear planar light valve, or LPLV. However, we can make arbitrarily large linear pixels as compared to the GLV to meet very high power demands. The pixels may then be focused down to create a linear pattern that is scanned across a media for material processing applications. Finally, the PLV may also be used as a phase modulator by altering the pixel surface to be purely reflective. This approach enables high-speed 2D fully holographic control through phase modulation, or even elements of combined amplitude and phase modulation formed by multiple mirrors. We have a number of modulators, controllers, and solutions based on our technology that are available right now. The high-speed buddy line, marketing part number F1088, is available for phase or amplitude modulation with a 25.5 micron pixel pitch. For amplitude applications requiring smaller pixel sizes, our Aurora line allows for pixel pitches of 5 microns. The G8192 has very high channel count for high throughput applications, while the new G2000's lesser channel count enables cheaper, more compact optics. We are very pleased to announce the beginning of our high-power linear PLV product line, the LP1088. This device enables high-speed, high-power linear amplitude modulation for wavelengths from UV to NIR. For all of our modules, we offer a Cosmo controller, which runs predetermined data. For high-speed buddy and LPLV lines, we have also developed a real-time controller. Finally, we offer eval kits of the GLV modules consisting of a modulator and controller. We have also developed a high-power LPLV optical head complete solution. Here we see our modulator lines. Please visit our website for more information. Our LPLV optical head is a complete high-power patterning solution in a box. It is capable of 500 watts output at 1064 nanometers with 100 kHz refresh rates. The video at the bottom showcases the patterning possible with this device. Please see our website for information as well as guidance on how to incorporate the optical head into a system. The Cosmo controller board offers the speed and flexibility needed for many applications or demonstrations. Pixel patterns are written to the board over a USB 3 cable, and columns of data may be called in frames at high speed. Pixel data and frame patterning cannot be written while the module is running. We offer a pixel download software to easily interface between a Windows-based computer and the board. For applications requiring real-time feedback, such as writing new patterns based on immediate data from a camera, we have developed a new real-time controller. The GOV controller is connected to a PCIe acquisition card for high-speed direct communication between the computer and module. Speeds may be limited by user hardware. The GOV and PLV technology is seen in many applications in use from industry and academia. Here we will go over some applications and how our products benefit them. Originally, the major application of the GOV technology was in displays. The high speed and contrast of the GOV allows for bright and colorful large format displays, and a 1D scanned image limits the needed laser power compared to a 2D projector. Examples of this technology in action include the Sony Laser Dream Theater at the World's Fair 2005 and planetariums powered by Evans and Sutherland. Future display technology, such as pocket projectors and near-eye displays, can further take advantage of the compact size of the GOV pixels as well as full phase control. Today, Screen Holdings has the #1 global market share of computer-to-plate or CTB printing. Their advanced plate setters are built on the back of GOV technology. The high power handling capabilities of the GOV, along with high speed and resolution, allows for a meter-long 2400 dpi aluminum plate to be prepared in less than a minute. Silicon Light Machine's experience in making MEMS technology means that these scanner devices are robust for thousands of hours of operation per device under high power and rigorous conditions in thousands of systems around the world. Another common application of the GOV is in direct write technology. The GOV's channel count and speed allows for high throughput maskless lithography. Screen's DW3000 takes advantage of the GOV to create 2 micron features at 65 wafers per hour at a power of 100 millijoules per centimeter squared. The GOV can be configured to create unique identifiers and geometries for every wafer. Additionally, Heidelberg Instruments uses the high resolution and bit depth of the GOV to create submicron features with their VPG maskless lithography system. On the left, we see examples of 2 micron down to 300 nanometer features on a 10 nanometer addressable grid from Heidelberg's VPG mask writer, as well as micron width curved channels. On the right, we see results from IMS chips, including 400 nanometer circles. Columbian Imaging Technologies uses the 1088 channel GOV in a direct write microlithographic system for holographic printing. With the GOV technology, their creation speeds have already increased by 10 times, with further improvements planned. High contrast and high bit depth with precise calibration enables products such as beautiful holographic labels and better performing diffractive optical elements. 4Pico Litho is another company that utilizes the GOV's high-speed contrast and channel count for high-throughput holographic origination. Their UV laser direct write system is capable of creating 3D microstructures with a critical dimension of 0.5 microns. On the right, we see examples of diffractive optical elements created using a GOV amplitude modulator. Researchers at UC Davis have applied the GOV to improve the resolution of a new OCT. This is done by using the GOV to shape the spectrum of a supercontinuous light source. The light from the broadband laser, whose original spectrum is seen in black on the left, is separated into its different wavelengths and projected onto the GOV. The GOV can then attenuate the individual wavelengths, such as to transform the original spectrum into a Gaussian spectrum, the red line on the plot. A Gaussian-shaped spectrum provides the best axial resolution. The GOV may also be used as a diffractive neutral density filter, the blue line, and optical low-pass filter, the yellow line. The effectiveness of this GOV-enabled spectral shaping is shown in the retinal images on the right. Notice the increase in sharpness of the edge, where before shaping there are ghost-like artifacts. This improvement allows imaging of important layers of the retina previously not possible. Researchers at UC Berkeley Center for Innovation in Vision and Optics have also taken advantage of the high speed and compact size of the GOV in their binocular tracking scanning laser ophthalmoscope. The GOV creates a line beam that is scanned across a retina, and the response is captured by a high-speed line camera. This application uses the new real-time controller to modify patterns based on the camera output, allowing real-time retinal tracking. This new tool will be used to investigate eye response questions that are especially relevant to the AR/VR industry. We have demonstrated the GOV in a laser marking system. By multiplexing laser power over many channels, we are able to create subsurface modifications at throughputs not possible with a single scanned beam. The GOV response is instantaneous grayscale, exactly modulating the desired amount of the power that reaches the surface. Additionally, we are very excited about the introduction of the LPLV for the laser material processing space. The extended aperture of the LPLV allows for even higher laser fluences and consequently higher throughput, with the LP1088 giving a 14 times gain in working aperture. The pixels are fully configurable, meaning even larger pixels can be created for higher power applications. For applications where every photon counts, a phase-based LPLV would enable holographic control to ensure that light is most efficiently patterned. Similar to material processing and laser marking, we believe the LPLV brings numerous unique advantages to high-power printing. The high-power modulator works with pulsed or continuous lasers, with modules available for wavelengths from UV to NIR, enabling any print technology with the LPLV platform. Unlike with beam scanning, an LPLV-based 1D scan system can have throughput speeds that are entirely agnostic to the print pattern. Your complex QR code or detailed logo can be created with the same ease as a simple letter. The optical head is ready-made for high-power applications at 1064 nanometers, including laser-based additive manufacturing techniques such as sintering and polymerization. Here we see a sintered layer being created by scanning the high-power output of the optical head across the material basin. Alternatively, the build platform may be moved, or both scanning the pattern and the media in conjunction can create expanded work areas. The finished part is shown on the right. It is indistinguishable from a traditionally printed 3D part and with a much faster build time. Phase control allows for holographic beamforming. Phased array-like operation has been demonstrated by researchers at Stanford University in collaboration with Silicon Light Machines. A linear profile may steer a beam's location in the far field or a focal plane. A circular or spherical profile imparts a lens power. These techniques can be used simultaneously for high-speed random access lateral and depth scanning. In this video on the right, we showcase the scanning capabilities of the phased GLV. A full-speed scan fills the screen, too fast to distinguish the scan line, though you can see optical surface reflections. The random access scan enables any scan pattern focusing on areas of interest. Point-to-point speed is agnostic of angular distance, as the ribbons are moving a couple hundred nanometers at most. Here we see the full scan slowed down. Diffraction orders are not blocked for this demonstration. Finally, for depth scanning, note that the bottom closer screen is in focus at a different time as the farther screen. The application of beam scanning for LiDAR is especially exciting, as the phased GLV allows for very narrow ribbons for high diffraction angles. The reflective nature of the devices also means that it may be used for both send and receive. Collected light can be directed by the GLV to the detector, with unwanted light directed away. Researchers at Stanford University have also used the GLV for different light sheet microscope modalities. In the configuration on the left, the GLV acts as a complex modulator to pattern and pivot a light sheet. The structured illumination of the pattern light from multiple angles allows for enhanced background rejection and shadow mitigation. In another configuration on the right, the phased GLV acts as a depth scanner, sweeping a tight Gaussian waste across the field of view. By synchronizing this scan with the rolling shutter of a camera, beautiful 3D light sheet sectioned images with high isotropic resolution can be captured in record time. The full possibilities of ultra-high-speed phase modulation with real-time control are just beginning to be explored. Researchers at CU Boulder demonstrated 1D wavefront shaping in order to image through a complex media, enabled only by the high speeds of the phased GLV with real-time controller feedback. This research has implications for imaging through scattering surfaces, such as turbine media, and for multimode fiber-based in vivo imaging by focusing light through the length of the fiber. In conclusion, the grating light valve is a mature MEMS technology that enables high-speed analog grayscale amplitude modulation and phase modulation with high power handling. The planar light valve takes the advantages of the GLV and adds a larger aperture with more pixels and 2D control, or bigger pixels for higher power linear control in the case of the LPLV. We are excited by the many emerging applications for our technology and look forward to hearing from new potential partners. Please visit www.siliconlight.com to contact us and learn more. Thank you for watching.